In this lecture, we will discuss about the topic of convolution, namely the mathematics of convolution. Uh, and we will actually start from where we left off in the previous class. Uh, as far as I recall, this is the part where we were at. And I will also, and even though we have discussed about the input side algorithm in the previous class, I'll still discuss about this again uh, as just to keep the flow. Okay, so let us start. As we have said, the last part of our lecture mainly discussed about the output side algorithm and how the equation basically allows us to think of it as a convolution machine. And the convolution machine, by the term convolution machine, we basically mean that the input can be kept fixed, and here you can actually keep the input fixed while considering the impulse response as a sliding window. You have to flip the impulse response and slide it around with the input, and just by taking this weighted sum of the inputs, you can get the each of the values of the output. So we will actually delve deeper into what this means when we see the example of the output side algorithm. But for now, this is just the theory of it. So you'll notice that when you actually follow the output side algorithm, you'll see that there will come a problem where you'll have to when you line up the samples, even in the input side algorithm as well, when you line up the each of the samples with the corresponding flipped version of the impulse response for the input side algorithm, the flipped version of the input, you'll notice that there will be some values which won't exist. Then some of the values will line up with values that do not exist in your signal. For example, here these values do not exist inside the impulse response, and here these values do not exist in the input signal. So in either cases, there will be some non-existent values. So how do we actually get rid of this, or how do we tackle this problem? Uh, Here, the approach that is mentioned is by reinventing the non-existent samples. Or in other words, is also known as padding. By padding, we mean that we simply fill in the values with zeros where there is no value. For example, here there is wherever there was no value, we had to pad some extra zeros. And actually, all signals have some zeros all the time, but we do not show them. We only show those parts where there are the significant amplitudes. That is what we actually define as our signals. Otherwise, every signal would actually be infinite. But we only take them as finite because we only take the values that we care about. Here, 1 to 3, these are the amplitudes that we care about. But we can have infinite zeros to the left and infinite zeros to the right. But we only take that many zeros that we need for our input side algorithm and output side algorithm. And now the question is, how many zeros do we have to pad? I mean, how do you know how to pad? What your padding criteria will be? It actually depends on which algorithm you're following. If you're following the input side algorithm, you'll have to pad using you'll have to pad exactly n minus 1 zeros. And here n is basically the number of points in the input signal, which is 4. So there are 4 points in the input signal. You'll have to pad, and 4 minus 1, that is 3 zeros to the left and 3 zeros to the right. And if you're following the output output side algorithm, then you'd have to pad m minus 1 zeros. Since m is and here m is the number of points in the impulse response, not the input signal, but the impulse response. So m is 3 here. So you'll have to pad 3 minus 1, that is 2 zeros to the left and 2 zeros to the right of the input signal. Notice that whichever algorithm you follow, at the end of the day, you'll have n plus m minus 1 points in the output signal. Okay. So this is the main idea for padding. We'll go into the details of how this padding helps us later on and what we actually do after that. But before that, we'll talk about some of the theories that are still remaining. Okay, there is an important part to notice here, that is the far left and far right samples in the output signal are based on incomplete information. Uh, and in DSP jargon, we actually term this as the impulse response is not fully immersed in the input signal. So the impulse response is normally we use M, capital M, just like I said before. M will be the number of points in the impulse response, and N is the number of points in the input signal. So the thing is, the impulse response, the first and last M-1 samples in the output signal are based on less information than the samples in between. You'll notice that when you actually talk about uh, the output in both cases, you'll see that the first M-1 points, uh, the first M-1 points here are actually not being not using all the values. I mean, they do not line up completely in the input signal and the impulse response. Okay, so no, not these values. The first two values here, since this is the impulse response, so the first two values here and the last two values, actually they do not line up. All of the values do not line up with the input signal. You'll notice that here only the first value lines up. So you're getting what you're supposed to get here. Here two values line up and the rest two values do not line up. We have to pad them in, we have to fill them in. So when you're calculating this value, this is actually coming from the two values that actually line up and two values that do not line up. So this value is actually coming from incomplete information. So similar to that, here only one value is coming from the input signal and the rest one do not match up with the impulse response. So this one is also from incomplete information. This one is coming from incomplete information. This one is also coming from incomplete information. So these two first two significant values. I'm not talking about the values that do not exist anyway. So these are also not coming from. These are also coming from incomplete information, obviously. But even then, these two values that actually are non-zero, these are also coming from incomplete information. As you can see, they do not match up completely with the impulse response. All the three values of the impulse response do not match up with the input signal. But here, this value is coming from all three values of the impulse response. So this value is based on complete information. This value is also based on complete information, even though it is coming from a value that does not exist in the impulse response. The other three values are being used to calculate this value. So this is coming from full information. But again, this one, these two are not coming from full information. If you notice, when you are calculating 17, it is coming from 0 times 1, then 0 times minus 2, then 3 times 3, then 2 times 4. But this one value from the impulse response is not getting used. You can consider that there is a 0 here. So it is not getting used to calculate 17. So this one is also based on incomplete information. So is 12 using the same logic. So this is what it means. Also in the output side algorithm, it is easier to visualize. Here it is a bit difficult because the first three ones are incomplete information anyway. And here the first two are incomplete information. Here the last two are incomplete information. In the output side algorithm, we have fewer output values anyway. As you can see, there are 3 before, here are only 2. So these are, you can ignore them. But here, even here, you'll see that the first 2 output values are coming from incomplete information. Here you have to look at these rows. If you look at these rows, you'll see that 1 is coming from 1 here, but 2 and 3 are not being used. 0 is coming from 1 and 2, but 3 is not being used. 2 is coming from all 3 as they totally line up with the input signal. 4 is also coming from all 3 because they are totally inside the lineup with the values in the input signal. But 17 again does all the values of the impulse response do not line up with the input signal. As you can see, 1 does not line up with anything from the input signal. Here we have to pad in the values. Okay, 2 and 3 lines up with 3 and 4, and here 2 and 1, both of them do not line up. Only 3 lines up with 4. Okay, so this is just the basic idea that the first few first m-1 and last m-1 values in the output signal y will not be based on complete information. And by this this is the term we mean when we say this. The impulse response is not fully immersed in the input signal. Okay, and now we move on to the mathematics and basically the equation that we have been talking about, and how we will translate it, how we will actually use this equation in pen and paper to solve convolution in pen and paper, because otherwise this equation is only useful for writing code. You can write a code that will compute the convolution between of an input signal with a impulse response h, but when you are doing this in your head, calculating all of these things, how you will actually execute this loop, how you will calculate this equation. So we have already shown this, how you will be doing this, but there is also another way without this table and method. We'll also talk about it. Okay, so the first thing that you need to know is for an endpoint signal running from 0 to n minus 1, and hn is an endpoint signal running from 0 to m minus 1, the convolution of the two will be an n plus m minus 1 point signal. We have already talked about this before. So, and we will actually consider their indices to run from 0 to n plus m minus 2. And you can already see why I'm using n plus m minus 2 instead of n plus m minus 1, because we are starting the indexing from 0. Okay, so we are also, we are considering the origin point to be 0, so that is why the indexing will be 1 less than the number of points. Okay, and how you calculate the output side algorithms, each of the values, is that basically the output side algorithm considers the output signal points, how each of the signal points are coming from multiple input signals. We have already said this before. Okay, so here we define the equation in this way: yi equals summation of hj xi minus j, and j here runs from 0 to m minus 1. So how does I come into play here? What does I run from? I basically runs from 0 to m plus m minus 2. Okay, so I here runs from 0 to n plus m minus 2, and j here runs from 0 to m minus 1. So basically, and this equation is otherwise known as convolution sum. So how you can actually use this information without use this equation without drawing this entire table. So you can use this in this way. Suppose you already know that there are n points in the input signal, and here n is equal to 4, and there are m points. So as you can see, m is equal to 4, and m points in the impulse response, so m equals 3. And you know that in y there will be values from 0 to n plus m minus 2, n plus n minus 2. So without even drawing this table, what you can do is you can directly find y0, then y1, dot dot dot. You can find the final index. Okay, and just by using the equation, you can find the individual values, and by finding the individual values, you can get the whole signal when you just put them in order, in sequence. So the reason this is useful, why output side algorithm is actually more useful than the input side algorithm, is because you do not have to solve the entire table. You do not have to come row by row to solve all the values to get, for example, y7, this value is 17. This is what? This is y. If this is y0, this is 1, this is 2, this is 3, this is 4, this is 5. So in order to find y4, suppose I tell you to calculate only y4, not the whole signal, not the whole output signal. I just tell you to calculate y4. In that case, you do not actually have to go through all the rows in order to come to 17, to the value 17. You can directly put the equation, use this equation that I just mentioned in that book. You can just directly use that equation and directly find the value for y4, what it should be. And how you will be doing that? Okay, so what you will be doing is this. For every value of y, I mean y, for y there are values from 0 to n plus m minus 2, as you know. You'll have to find that many values for y. For any particular y, if you want to compute, you need all of h. You need all the h values. If you follow that equation, you'll see that the the indices for h, I mean the impulse response, runs from 0 to m minus 1. So the h values that you will need r h0, then multiply with corresponding x minus something, okay, x minus 0, then plus h1 times x something minus 1, then plus h2 x something minus 2. The basic idea is that you need all the h values there are. So if there are 3 h values, you need all 3 h values. Okay, but which x value you will use here? See that I have kept some space. So the thing is, which x value you will use will depend on which y value you are trying to compute. For example, suppose I'm trying to compute y4, which should be 17. Here I already computed all the things and got to 17. Now suppose I do not have any of these rows computed. I just want to find y4, only this position. I do not care about what the other position values are. I just want to find the value of one position. Now how will I do that? I'll just have to put in 4 everywhere in x. Okay, so if I put 4 everywhere in x, what does x4 mean? X 4 minus 0 is x4. So what is x4? X0 was this, x1 is this, x2 is this, x3 is this. So this is 3, this is 0, this is minus 1, by the way. This is minus 2. And remember that this did not exist. I had to pad them in. And this also did not exist. I had to pad them in. So the thing is, I'll always use all the values of h. That is for sure. No matter how long the h is, that long this equation will be. But the x values will be based on which value of y I'm trying to compute. So, and this equation is useful. As you can see, this is useful when you're trying to find only a single sample value. You do not want to find all the values. If you want to find all the values, you'll have to come like this using the tabular approach. But if you just want to find only one single sample value, you can use this equation. Use this format where all the h values will be there, and only those x values will be used based on which sample number you want to compute. Suppose you want to compute 4, then only x 4 minus 0, 4 minus 1, 4 minus 2. Only these values will be used. Okay. So how does it actually give you 17? You do not, you just want to use this equation and want to find this particular value. Okay, so how are you going to get that? So just notice that h0 is 1. And remember that even though this is actually flipped, output side algorithm makes it flipped. Also, the input side algorithm will make the input a single flip. In any case, it is flipped. But this is not actually the 0th position. This was the 0th position. This is the 1th position. This is the 2nd, 2nd position. Okay, so h0 is 1. h0 is 1 times x4 minus 0. What is x4 minus 0? So x4 minus 0 is x4, which is 0. Notice that it is 0, plus h1. What is h1? 2. So 2 times x4 minus 1, which is x3. So x3 is 4. 2 times 4 plus h2 times x4 minus 2. x4 minus 2 is x2, which is minus 2, and h2 is 3. Wait, is this correct? h4 minus 2 is, yeah, minus 2. Okay, minus 2 times h2 is 3. Okay. And 3 times minus 2 is minus 6, plus 4 times 2 is 8. 8 plus minus 6 is 2. Okay, how are we getting 17 here then? 0, 4 times 2. Okay, 3 times 3. Oh, wait. Oh, I made a mistake. So this should be 1. This is 2. Okay, so x2, I am using x2 here. So this will be minus 2, this will be 3. Okay, so this is 3. 3 times 3 is 9. So 4 times 2 is 8, plus 3 times 3 is 9. So 8 plus 9 is 17. So this is how we got 17. And if you follow the tabular approach, this is also the same value that you're going to get. So you're also going to get 17. But in order to get 17, you have to come step by step, row by row, and come to this particular position. So this is actually a shortcut kind of way to get any particular value for any particular sample of y. But if you want to find all the samples of y, it is better to follow the tabular approach, because this will give you all the values from 1, 0, 2, 4, 17, 12, all the values you are going to get. But this method is useful. This equation method is useful when I tell you to find any one particular value of y. Suppose there are like 21 values of y possible. If you want to calculate using the tabular approach, you would have to compute 21 rows, suppose. But and I just gave you to calculate y15. So are you going to go from 0 to 50 number row? Actually, that is very tedious. So it is better to remember this equation in order to just find the 15th sample. So this is easier. So that is why I always mention to use output side algorithm instead of the input side algorithm in these kinds of scenarios where you have to find any particular sample of the output signal. So this is more useful in this case, the output side algorithm. This is easier than input side algorithm. But the ultimate thing is the result will be the same, no matter which algorithm you use. Okay. So that was all about the mathematics of the two algorithms, how the mathematics of convolution is performed. Now we will go to the main difference that we have already said this before. So the basic takeaway, the summary, is that the main difference between these two programs, that is the input side algorithm and the output side algorithm, what do they do? The input side algorithm loops through each sample in the input signal, while the output side algorithm loops through each sample in the output signal. As you can see, the outputs in the output side algorithm, the equation is written in terms of y. Okay, all the h values are used, and we are calculating all the y values from 0 to n plus m minus 2. So that this is the main difference between these two algorithms. Okay, and nothing more of this chapter is of interest here. So we'll move on to the next chapter, which is the properties of convolution. And in the previous chapter, we mainly discussed about the mathematics of convolution. So here we come to some theoretical stuff about convolution, what it actually implies. Okay, the first thing is that some common impulse responses and what they actually mean for convolution. We already talked about delta function, which is the unit impulse. So the delta function can also be an impulse response of a particular system. Okay, so we said that hn is the impulse response of a system which it convolutes with any incoming xn to produce yn. Okay, so xn times hn is used to produce yn. So when you are actually passing xn through a system, this is what the system is doing. So this is the system. This is what the system is doing internally. It is multiplying with an impulse response. What if that impulse response is a delta function itself? That means what if hn is equal to delta n? What will happen in that case? What will happen is yn will basically be xn. That means xn convolution with delta n, xn convolution with delta n is xn. Okay, so the delta function is like the identity function, the identity operation. Convolution with the delta function is equivalent to the identity operation. So basically, this is what is said next, that this property makes the delta function the identity for convolution. Similarly, how 0 is the identity for addition, because adding anything with adding 0 with anything will mean that same thing. Also, multiplying 1 with anything will mean that same thing. So 1 is the identity for multiplication. Similar to that, delta function is the identity for convolution. Okay, and if you want to, if you do not use delta function directly, if you use a scaled one version of the delta function, if you perform scaling, that is k times delta n, what will happen is you will get an amplifier on attenuated system. So this is an identity system. This operation is performed by an identity system. This operation will be performed by an amplifier or attenuated system based on whether k is positive or negative. If k is positive, then positive greater than 1, then this operation, this convolution is performed by amplifier system. Otherwise, if k is negative, then this convolution operation will be performed by an attenuated system. Also, there is another version which is performing shift on the delta function. If instead of using delta function directly, you use a shifted version of the delta function like this. So that will be a delayer system. That so basically that system that performs this operation will be called a delayer system or an advancing system based on whether S is positive or negative. And I have already mentioned this before in the previous class. Maybe previous class, I don't remember, but I've already mentioned this before. That if S is positive, then n plus S, this is an advancing operation. If S is negative, then n minus S is a delaying operation. Okay. Okay, so these are just some graphical representations of identity, amplification and attenuation and all these things, and shifting and echo. Okay, so identity will simply be the delta function without any change. That means at the 0th sample, you'll have 1. Amplification will be at the 0th sample, you will have something greater than 1. For attenuation, this will similarly be something less than 1. That means some negative value. Okay. And for shift, this will only be, instead of at 0 point, it will be somewhere at other than 0. And for echo, it's a bit it's like a combination of two things. First of all, you perform shift. First of all, you have the delta function, plus you have a shifted and scaled down version of the delta function. So this is what an ecosystem allows you to do. It provides you the original xn plus a shifted and a slightly toned down version of the original signal. If you convolute this hn, if this is your hn, and if you convolute this with any xn, what you're going to get is, you're going to get the output signal will be an echo. You'll get the input signal also after a bit delayed, after a bit of a delay, you'll hear the signal again in a bit lower volume. And also convolution allows you to do some calculus like operations. Okay, it can allow you to resemble integration and differentiation, but usually we use the term derivative and integral specifically for continuous signals, but here we are talking about discrete time signals, so we give them a new name. Instead of derivative and integral, we call them the first derivative, and or otherwise is known as the we call it the first difference. The derivative is for continuous signals, so here we call it the first difference. Or for, similarly for integral, the discrete version is called running sum. Okay, and these two are actually expressed in the mathematical form in this way. So this is the first difference. The yn will be calculated by xn minus 1, and there is also another method to calculate the first derivative, which is yn equals xn plus 1 minus xn minus 1 divided by 2. So this one takes the midpoint into account, and this one takes only the current point and the previous point into account. This one uses the next and previous point to sort of like use the midpoint as the derivative. Okay, and in that case, how will this the graphical representation of this system look like? So what this system is basically doing is, it is convoluting with basically what I'm saying is how you will get this behavior for each of the output points. So how you will get this behavior is, if your hn is something like this, if your hn is a delta has like a delta function and also an inverted delta function, a shifted and inverted delta function. If it is something like this, then this is what will happen when you convolute this signal with xn. This is the yn that you're going to get. You're going to get this behavior for every point. If this is the hn you convolute with. Similarly, if this is the hn you convolute with a step function. So if your hn is like a step function starting at 0, then what you will basically get is, you'll get the running sum as the output. So this is what your output will behave like. Okay, so before that there is a thing, and I'm going to actually talk about what this thing actually is talking about. So using this approach, each sample in the running sum can be calculated by summing all points in the original signal to the left of the sample's location. So the basic equation would have been something like this originally. It should have been yn should be calculated by using all the xn values before this. So I equals to minus infinity to n. That means before the nth point, the points that were there, we will have to use all those, sum them up to get this particular value of yn. So notice that there is a problem with this implementation. So that is why they showed it like this, because this is a lot more efficient than this. When you are using this equation to calculate each yn, what you are doing is you will have to you are actually recalculating lots of values that you calculated previously. For example, when you're calculating y1, you are getting x0 plus x1 to get y1, to get y1. And actually there are x minus 1, x minus 2, all those values consider that they're all 0 anyway. So in that case, the very first single point that you want to consider is x0, then x1, then for y2, if you wanted to calculate y2 now, you would have to recalculate all these points again, right? You'll have to use x0 again plus x1, which you calculated in the previous for the previous sample anyway. For y1 you calculated them before, but now you're recalculating them and you're adding them with x2 to get y2. So notice one thing, this whole thing can be replaced by yn because it was used to calculate y1, because it was used to calculate y1. So x0 plus x1 can be used to represent y1. Similarly, any nth point can be calculated using the xn plus yn minus 1. This is why the equation is like this. This is a lot more what can I say, a lot more efficient version of this equation. Okay, so this is what the running sum does. And even though this is just the mathematical representation of the running sum, what would be the corresponding hn? You would have to convolute to get this thing. So this is the corresponding hn, a step function. The hn would be a step function, and in this case, for calculating the first difference, the hn is not a step function; it is a delta function plus shifted and inverted delta function. Okay, so that is the two hn you need to remember for performing first difference and the running sum. Okay, and also convolution allows you to design filters. So when we actually perform filtering on any input signal, what we are really doing is just performing convolution of the input signal with some hn, and that hn will basically define whether this filtering is a low pass filtering or a high pass filtering or whatever type of filtering it is. So here we'll just we won't go into the depth of filtering because we have a specific chapter for filtering. Later on you'll see, I'm not exactly sure what the chapter number is. You can look it up. There is a chapter later on which we'll discuss after mid. This is the near the end of the course. We'll talk about filtering, and there we'll delve into the details of filtering. Here you just need to know what is the hn for getting a particular type of filtering. Okay, so in general, just the thing that you need to remember is a low pass filter kernel are composed of a group of adjacent positive points. So the hn for low pass filtering would be a bunch of adjacent positive points, something like this. If it is an exponential low pass filter, then it would be something like this. If it is a square low pass filter, square pulse low pass filter, then it would be something like this: 0 in a particular area, but some positive values in a small region. So this would be the low pass filter, an example of a low pass filter. And if you have these positive values extended, that means even from -1, if you start the positive values, and if you extend it up to 15, so then what you are actually doing is you are controlling the cutoff frequency. Okay, so we do not need to actually know the details of how this is happening, how extending the positive values in the left and right allows me to change the cutoff frequency. We just need to know that the positive values define how much frequency I am going to allow to pass. If it is narrow, if the positive value range is narrow, then the cutoff bandwidth is narrow. Otherwise, the cutoff bandwidth is extended if I extend the positive values. Okay, so what it actually does is when you convolute this type of hn with any input signal xn, it performs smoothing on the original signal, thereby removing high frequency components. Okay, and the use of low pass filters is usually seen in these kinds of applications, that is for noise reduction, signal separation, and wave shaping. Also, this is also another low pass filter called the sync low pass filter. We'll discuss on them in more details in some future chapter. Okay, and now we move on to, so these are examples of high pass filters, and how are they different from low pass filters? We will be talking a bit on that. So there is a common strategy in filter design to get high pass filters. Okay, not just high pass filter, any pass filter you can get by at first designing the low pass filter, then doing some operations of that. So first you devise a low pass filter and then transform it so that to whatever you need. So in this case, we'll just be talking about the high pass filter. To understand this, what you'll need to know is that the original, if you just perform convolution with a delta function, you would get xn, right? So xn perform convolute with delta would give you xn, and here what we are seeing is for the low pass filter, xn convolute with the hn of a low pass, h, suppose this is l is for low pass, convolute with this, you get those parts of x that are with low frequency, you get xn. So by the superposition principle, you get an idea that xh, the high pass components, if you add them together, you're supposed to get x, right? You're supposed to get x. So what should be the corresponding h? That means the high pass filters h should be, in order to get this, what do you think? This will simply be that if you perform delta minus hl, you're going to get hh, right? I mean, this just comes from common sense, that the corresponding hh that you would need will simply be a difference of delta function with the hl. So if you perform a difference of the delta function with the hl, what you get is hh. So this is how you actually got these things. Okay, these things. So all of these are basically difference of the delta function, that is unit impulse, with this signal values, that is HL, the impulse response for the low pass filter. If you take the difference, you get the corresponding impulse response for the high pass filter. So it was so the originally what was supposed to be here is in the low pass filter. If you look at this, it was the first point at 0 was something greater than 0.2. Suppose this is 0.21, and if I take the difference of this point from the impulse response, unit impulse, what am I going to get? The unit impulse was 1. So 1 minus 0.21, you're going to get something like 0.79. So this is what you got, 0.79. Okay, so this a bit lower than 1. This is 0.79. So in this way, if you take the sample wise difference for each of the points, you get the remaining points. So this is how you got the high pass filter for the exponential case. Similarly, the high pass filter for the square pulse case will be something like this. Similarly, for sync, it will be something like this. There will be only one point positive and all the points are negative. Also, there will be only one point positive and all the points are, the rest of the points are negative. So, and that one point is actually at the 0th position, because you're taking difference from the unit impulse, and unit impulse has 1 in the 0th position, and everywhere else it is 0. So remember, only at the 0th position you're going to get the positive point. Everywhere else will be symmetrically negative. Not symmetrically, it will depend on the corresponding low pass filter. As you can see, this is not symmetric, but this one is symmetric and this one is symmetric. Anyway, so this is how you get high pass filter from low pass filter. Okay, so these things are not necessary. You'll notice that I did not mark anything from here. The causal, non-causal, and zero phase, linear phase, non-linear phase. These are not necessary. We can directly go to the mathematical properties of convolution. So the first thing is that we have already said this before. That is, convolution is a commutative operation. So convolution has the commutative property because if you perform an with bn, or in other words xn with hn, this is similar to performing HN with XN. So it does not really matter which one is the input signal and which one is the impulse response. If you flip it, if you consider the input as the impulse response and the impulse response as the input, then the final output will be the same actually. And also convolution also has the associative property, and this associative property is actually useful in getting how cascading, describing how cascaded systems behave. We had already talked about what cascaded systems are. That means you chain together one system after another. Then how will their behavior be like? So that is actually defined by the associative property. As you can see, if you take a signal and pass it through a system so that it convolutes with something, suppose Bn, or consider this as H1, it convolutes with H1, and then you pass the whole thing, the output, to another system that performs convolution with H2. Okay, so this is equivalent to passing the input to the combined system. So in this case, you passed it through one system, then another system, and this is actually equivalent to taking the two systems together, performing their combined operation, and then the combined system, if you pass the input through that, is going to be the same, provided that the system is LTI, linear time invariant. Okay, so this behavior actually comes from the associative property, and this allows you to define how cascaded systems behave. Also, there is another property called the distributive property, which allows you to define how the parallel systems will behave. Okay, in parallel systems, what do? You pass the same input AN through multiple systems, right? So you pass AN through multiple systems, and then you this is what parallel systems are like. Okay, so you pass AN through multiple systems, such as this convolutes with B, this convolutes with C. This is equivalent to passing them just like this. AN can be passed directly through the combined system, that performs AN plus BN. Not just this, it will also include the plus also. So it does B, C plus, and then it convolutes with that to get the result. So the result will be the same in both cases. The result here, the result here will be the same. So this comes from the distributive property, and this one explains how parallel systems behave. Okay. Also, there is another thing called transference between input and output. So imagine a linear system receiving an input signal X and generating an output signal Y. Now suppose the input signal, you are changing the input signal so that it is attenuated or amplified, or if you perform some derivative, some first difference on the input signal, and then if you pass it through the same system, what is going to happen is the output is also going to get changed in the same way. So if you read through this paragraph, this is what it basically says. So the basic question was, how does the change in the input signal relate to the change in the output signal? The answer is, the output signal is changed in exactly the same linear way that the input signal was changed. For example, if you perform amplification on the input signal, the output signal will also be amplified by the same factor. Okay, if you take the derivative of the input signal and then pass it through the system, you'll see that the output will be the derivative of the original output. Okay, so before you perform this, if you pass X through the system and you get Y. Now if you perform something on X and change it and you get Y, you'll see that this Y prime will basically be the same operation that you did on this X. So if you perform a derivative, if X prime is a derivative of X, then Y prime will be a derivative of Y. Similar to that, if it is an amplification, then that will also be an amplification. So this is just what is said here, and this actually comes from the associative property. If you think about the associative property, then this will be clear. And there is also another thing called the central limit theorem. I don't know if you guys have heard about this or not. You might have heard about this in your probability course. So in any way, so this is an important tool in probability theory because it explains why Gaussian probability distribution is observed so commonly in nature. So what the central limit theorem says is that if you perform convolution of a signal with itself many times, So in the long run, you're always going to get a Gaussian. Okay, so whatever the signal is, suppose it's a something like this. Okay, so these are the points. So these are the points, some discrete points along the time axis. You define some discrete points. Okay, and there are actually this infinitely to the infinite left and infinite right, all are zeros. So if you convolute this signal, suppose this is x. If you perform convolution x with x itself, then again x with x itself, it will gradually look more and more like a Gaussian. So this is what it says, the central limit theorem. So this is one of the properties of convolution. So convolution has the property of gradually moving towards a Gaussian like distribution. The more you perform convolution with itself. Okay, as you can see, there is an example here. This is xn. If you perform xn convolution with xn, this looks somewhat like Gaussian, but not fully yet. If you perform it 4 times, you see that it looks almost fully like a Gaussian. And if you perform it even more times, it will look, the changes will be reduced. It will be almost like this, but it will look even more like a Gaussian. And at one point, there will be no change. It will be fully Gaussian. So this is just what it says here. The width, notice that the width of the resulting Gaussian will be equal to the width of the original pulse. Okay, so whatever the width was here, from -5 to something a bit more than 5. So the main width of the Gaussian will follow this, and after that particular width, you will see that it exponentially reduces towards 0. Okay, so the positive values of this Gaussian will be mainly in this width, that follow the width of the original signal. Okay, and after that particular width, it will exponentially go to 0. Okay, so that was all about the properties of convolution. Now we move on to another operation, an entirely new operation called correlation. And it is not actually entirely new because it comes from convolution itself. So correlation is just, you can think of it as convolution with inverted impulse response. Okay, so if you remember, convolution performs inverting by itself. The impulse response was 1 to 3, but during the algorithm of convolution, it performed the impulse, the inverting according to the algorithm by itself internally. It performed the inverting. So correlation, what it does is it performs convolution without the inversion. So this is just like if you send the inverted version of the impulse response through the convoluter, through the convoluting algorithm, convolution will perform the inversion internally. So the inversion, the p inversion is getting cancelled. So you get 1 to 3 instead of 3 to 1. Okay. So this is what it basically means. This is what correlation actually does. So correlation is a mathematical operation that is actually very similar to convolution. Just as with convolution, it uses 2 signals to produce a third signal. And the third signal actually is called cross correlation if it is a different signal than the original one. So if you are performing xn correlation with, I actually forgot what correlation is denoted as. For convolution, we use this. For correlation, I think it is denoted as something like this. I'm not exactly sure. I'll talk about this later in class. Okay, so if you perform xn with hn correlation, then it is called cross correlation when it is a different signal. But if you perform xn with xn, then it is called autocorrelation, correlating with itself. So that is called autocorrelation. Okay. So the thing is, there is an example given here, and it is actually recommended, even though I did not discuss about this whole thing. It is recommended to go through this example to get a better idea of what correlation's use is. So convolution's use is, we already said what convolution is used for. Convolution is used for getting the output of a particular system. So the output is generated by convoluting with the impulse response. But correlation is not used for that reason. Correlation is used to find the similarity of a signal inside another signal. Okay, so the basic idea is this. Suppose there is a radar, and from the radar you are emitting audio or maybe a radio signal. Okay, so you're emitting a radio signal, and that radio signal goes uh, through the space, through vacuum, and it hits something, maybe a planet or maybe something, an object, a flying object, and it comes back to your radar. So what the radar is going to get is just its own signal. If there is something along its direction, what it is going to get is its own signal, but only a shifted version of its own signal and a bit attenuated version of its own signal. Okay, so how will it actually detect that something came from somewhere, that its own signal got reflected? How will it know? So how will it know is it will basically perform correlation. If it performs correlation and at any particular point it sees a big spike, then it will know that there was something along its direction. Okay, so suppose the signal that it transmitted was this. Okay, and the signal that it got later on, the received signal, is something like this. Okay, so there were a lot of noises, but at one particular point it got its own signal back. Okay, so when it performs correlation between these two, then so what it will do is it will just use this and it will slide this around. At one particular point it will fully match, it will directly align. In all other points it won't align much, so it will be gibberish, but at one particular point it will align fully. Okay, so this shape will fully align with this shape, and there will be a huge spike in the output. When you perform correlation between them, there will be a huge spike in only one point of the output signal. Okay, so that point will determine that there was something along its path, and that is why you're getting a spike, because you just found an entire correlated component. Okay, so and the point at which the spike occurred, that point will tell you that the correlation was found at that sample number. That means at that particular time interval you got the correlation. So you will know, based on that time difference of receiving the matching signal, you will know that this amount of time delay occurred, means the other values can also be derived based on the values of the velocity of the sound and all the other things. You can calculate the other values as well. Okay, so the basic idea, I think I already discussed them, but here you can read through this. The amplitude of each sample in the cross correlation signal is a measure of how much the received signal resembles the target signal at that particular location. And as I have said, if you perform cross correlation between two signals, what you're going to get is you'll find peaks at that location for every location where there is a match of the signal inside another signal. So if if this peak is found here, then you'll get a peak here. If this signal is found somewhere in this signal, then you'll get a peak here. But if there are multiple places in this signal where there is a similarity, you'll get peaks in all those places. Okay, so this is basically like you can actually consider cross correlation as a kind of search function for signals. Just like we have search functions for finding some values inside an array. Maybe you use, I think you guys use linear search or binary search to find any particular value, whether it is inside an array or if it is inside the array, in what location it is in, the index location. So those kinds of search functions allow you to find those things. So cross correlation is also something like that. It is a kind of, you can think of it as a function for finding a signal inside another signal. It will give you spikes in all those places where there are match. That is, the signal is found in all those places. You'll get spikes there. Also, you'll notice another thing. That is, if the target signal contains samples with negative value. Okay, so if you're trying to find this signal inside another signal, so if it contains negative values, then you should also have, if you are trying to find this signal in this particular signal, it should also have corresponding negative values in this place as well in order to find a match, right? So if this is negative, and here also there are large negative values here, so what you'll see is that ultimately, since you're performing correlation, and correlation is like element wise multiplication and sum them up, so what you'll get is negative times negative, you're going to get positive. So the result of correlation is always positive. This is what is basically said here. Okay, so imagine that the correlation meshing is positioned such that the target signal is perfectly aligned with the matching waveform. That means you are in that location where it is aligned. Okay, and samples from the received signal fall into the correlation machine. That means they directly match up, and they are multiplied by their matching samples in the target signal. Okay, so you are multiplying negative value samples. Notice that we initially said that the target signal contains negative values. Okay, so what will happen? You are multiplying negative values with negative values, resulting in positive values. So also, if you perform positive with positive, you're also getting positive. So the final summary is that no matter what you do, you're always going to get positive peaks in case of correlation. The peak is always positive. Okay, and another thing is that the peak generated in the cross correlation signal is symmetrical between left and right. And this is true even if the target signal isn't symmetrical. And this is actually very easy to notice. I mean, just think of it in this way. When you are considering this target signal and sliding it around to find where it matches in this signal, in this received signal, when you're trying to match it, what happens is, suppose this particular point, okay, this particular point, when it is in here, it gets multiplied with the first point. The last point gets multiplied with the first point here. Okay, and you're going to get something for this. And when you slide it around so that it comes here, so that the first point of this multiplies with the last point of this, notice that the same response will be produced here as well. Here the last point of first is getting multiplied with the first point of the second. Okay, so the last point of the first is getting multiplied with the first point of the second signal. And when you slide it around a bit, then after it near the end position, the first point of the first gets multiplied with the last point of the second. So here the response will also be the same. So as you can see, whatever response you got here, you're also going to get the same response here. So from the middle, in the middle, it is going to line up with this value with this value. So you're going to get a peak here. And to the left and right of the peak, you're going to get symmetrical responses. Even if this shape is not symmetrical, and this shape is not symmetrical. Even if they are not symmetrical, you're still going to get the final output will be symmetrical around the peak. So this is what is said here. Okay, and also another thing to remember is that cross correlation is not trying to detect the target signal. It's trying to detect the target signal but not recreate it. That is, you are trying to find where the matching is found, but you won't be able to know what the shape of the original thing was. So the thing is, this signal you only got, this is the one you sent and this is the one you got, but the signal that you got, by looking at this, you know that this is where this is actually resembles this particular signal, but the system itself won't know the shape of the signal. Okay, it will only get a bunch of noise values and some amplitude, some large amplitude values. So wherever it finds the correlation to have a peak, it will know that that is where the signal actually matches, but it won't actually detect, it won't actually recreate the original signal. Okay, so the peak value gives you the location of the signal, but it does not give you the shape of the signal. But if the original signal is known to you, such as this, then you can get an idea that since I'm getting a peak here, there must be something like this in this location. So this is just kind of common sense. Okay. Also, there is another name for this, for using correlation like this. It's called match filtering. And this is not useful in our current scenario. This is useful in some other chapters, as it is mentioned here, but we won't be using this anyway. So this is just a heads up. Okay, and another thing, just to something that I mentioned before, there is the correlation machine and convolution machine are identical except for one small difference. That is, in case of convolution, the impulse response was flipped left for right. If you use the output side algorithm, which is more convenient to remember and use, we always talk about output side algorithm mainly for this reason. That is because, and if you follow that, you'll see that the impulse response was flipped left for right. So this was just a step that was performed during convolution by default. So if you use the same convolution machine in order to perform correlation, what you have to do is you have to pre-flip it. If you pre-flip the impulse response and then pass it through the convolution machine, the convolution machine itself will flip. So the pre-flipping and flipping will cancel each other, and you'll get the effect of correlation. So convolution machine can be used to perform correlation. So this is just the basic gist of this entire section. Okay. So in the correlation machine, this flip is not supposed to take place, and the samples are supposed to run in the normal direction. So this is what is supposed to happen in the correlation machine. So if you want to use convolution machine for correlation machine, you can do that as well. For that, you'll just have to pre-flip it. So the signal reversal is the only difference between these two operations. So it is possible to represent correlation using the same mathematics as convolution. This requires pre-flipping one of the two signals being correlated. So the left or right flip inherent in the convolution is cancelled out. Okay. So what you will be representing this in terms in mathematics will be something like this. If this is convolution, A n convolution B n produces C n. So the correlation will be something like A n convolution B minus n equals C n. Okay, so this would be the correlation result. C n in that case would be the correlation result. If you perform convolution with the inverted B, that is B minus. Okay. So that is all about what correlation is. So now the final topic is the speed of convolution. That means what we care about convolution. When we do convolution, what we really care about is the performance of convolution. So what affects the performance of convolution? If you notice both the input and output side algorithm, you see that convolution is basically a bunch of multiply accumulate operations. Okay. So what you're doing is, when you're doing all of this, what you're doing is you're multiplying and adding up the results to get each of the values, right? So this type of operation is called a multiply accumulate operation. So this is the basic building block in DSP, and this operation is actually used for multiple things. First of all, for convolution, this was used. Also for DFT, that is discrete Fourier transform. You'll see that the same type of operation is used, multiply accumulate. So that's why it's called a building block of DSP. Okay. In case of convolution, you'll see that a signal composed of n samples is convolved with a signal composed of m samples. There is an impulse response of m samples. So the total number of multiply accumulate operation that you are doing is n times n. Okay. So that means the complexity of convolution is big O of nm, where n is the number of samples in the input signal and m is the number of samples in the impulse response. Okay, so it is big O of nm. Actually, it should be capital N, because we are always using capital to represent the number of points. Okay. Okay. So this is what is the time complexity of convolution. And notice that if the input signal is of 10,000 samples and the impulse response is of 100 samples, usually this is what happens in most cases. I mean, it is supposed to be large, right? In practical scenarios, your input signal will be huge, even more than 10,000 samples. And suppose your system, whether it is a filter or whatever it is, even if it has low number of samples compared to the input signal, still it will be somewhat huge. Okay, 100 or 1,000 samples. So if you multiply them, you'll see that the result is going to be quite large. For more input samples, if there are more points, it would have been even more, like in order of millions. So that would take quite a lot of time to perform convolution. If you are performing filtering, you'd have to perform the convolution, right? So in that case, it would take a long time to perform the filtering. So usually what happens is, this type of excessive execution time is commonly handled in one of three ways. So the first is to simply keep the signals as short as possible and use integers instead of floating points. So in most DSP systems, there are some pre-built mechanisms to handle integers better. I mean, they handle integers faster than they handle floating points. So if your signal has some floating points, like maybe 101, 1.01, then another value like 2.5, it can be 2.52. It can be done that you can actually consider you can actually round them down or up to a particular integer. So what you can do is you can take 1, then 3. Okay, you can take these integers, you can take an approximation of the input signal and perform the processing on this approximated signal. So that will give you a bit. It will make it so that some things will be a bit distorted. Your output signal will not be exactly what it was supposed to be, but still the processing will be done faster. Okay. So this is one way to do this, and the second method is to use a computer or a processing unit that is specifically designed for DSP, similar to what we defined for computer graphics. If you remember, in computer graphics, we said that for these kinds of operations, we usually use GPUs, specially built GPUs. That is why NVIDIA and AMD have specially built GPUs that can handle graphics things well. That is why we have graphics cards. We do not use when we use CPUs to calculate the same thing. It takes a lot of time. So GPUs are specially built for those kinds of applications. Similar to that, there are specific computers or systems or units in specific hardwares built for performing these kinds of things, DSP things. Okay, so which allows you to do multiply accumulate operations faster, just like GPUs perform matrix operations faster. So you can use that. So that is just another solution. And also the third solution is to use better algorithm for implementing the convolution. Instead of using the output side and input side algorithm for convolution, even though that is useful, we can implement it for small convolution or for doing pen and paper work. But for large signals, you cannot execute the whole loop like that. So for that, we have some specially built algorithms. We won't be talking about those things in details in our course, but just for our knowledge, you should know that there is something called FFT convolution that uses the fast Fourier transform. That means it performs convolution in the frequency domain. When you take the signal in the frequency domain and perform some operations there, it becomes easier perform the convolution. Okay, so this is just the third way to do this same thing. So the signals with low number of samples, the FFT convolution and the normal convolution, that is this procedure, won't be much of a difference. There won't be much of a difference in terms of the performance for small samples. But if there are large number of samples, then you see that the FFT convolution can be hundreds of times faster than the normal convolution. That means the difference becomes noticeable. The performance difference becomes noticeable. So that is all. That is all for our chapter regarding convolution. We have discussed about the mathematics and also the theory regarding convolution. So that will be it for our discussion about convolution. So I'll be stopping my screen share now.